Okay, so where we left off here then, we were just going through some last few examples on concavity in the second derivative test. I just want to go through a few and walk you through a couple more issues that can pop up when you're applying the second derivative test. And then if there's any time left over, I mean, if there is, it won't be much, but if there's any time left over, you guys can work and just ask individual questions. Okay, so here's kind of where that's not working, is it? Darn it. Here's where we left off. Okay, we were doing a problem here. We were trying to locate all the critical points of this function. We're going to want to find local extrema. And while we're at it, let's go ahead and find points of inflection. Okay, so we started this one. We had a polynomial. So we know that the domain is all reals. We knew that, write that down. That's the case for every polynomial. We know there's no symmetry because I've got a mixture of even and odd exponents, so unfortunately I can't take advantage of that. And then I just took the derivatives, right? And we were in the process of trying to locate the critical numbers. So we had started, we took the first derivative. We know that it's nowhere undefined, but we could get critical numbers where it equals 0. Okay, and so we were in the process of trying to solve this polynomial equation. This is some really good algebra review, okay? So suggestion was made, we've got 4 terms here. So can we factor this by grouping? When we've got an even number of terms, we can always factor by grouping, right? We can't always, but that's our maybe our first avenue that we're going to attempt to try to find solutions with. And we can sort of tell in advance if that's going to work because we can look at the coefficients. If the ratio of the coefficients in the first group is equal to the ratio of coefficients in the second group, then we know that this is going to work out. So here we've got a 1 and a -4. So 1 to -4 is the same as -16 to +64, isn't it? Right? So we can see this is going to work. And even if you didn't see that, we could always just try factoring by grouping. Either it's going to work or it's not. So if we split this thing into groups, we've got group 1 and group 2. So if we factor out the GCF from group 1, what is that? What can I factor out from group 1? Just type it in chat, somebody, everybody. Somebody say something. Can I hear somebody say something?
Can you hear it?
Yeah, I can. Okay, good.
You pull in x squared out of the first one and 16x out of the second one.
Okay, so remember, we're going to pull, now when we do this, we're going to work on the first group first. So we're going to factor out an x cubed. And then we have to figure out what's the remaining binomial. So if I factor out an x cubed, or sorry, an x squared, right? Not an x cubed. What did I say, x cubed? I don't know. I can factor out an x squared, leaving me with what? Well, x minus 4, agreed? That's my remaining binomial when I factor out the GCF. Okay, so then in the other group, I'm going to have 2 parts to that, right? I'm going to have something that I factor out, and I've got my remaining binomial. And remember that the remaining binomials need to be the common factors in the 2 groups. Those always have to be the same, right? So if my remaining binomial in the first group is an x minus 4, I'm going to force that onto the second group, and then I'll just see, does that work? Is there something I could factor out of the second group to get a common binomial factor? And there is. I could factor out a -16, right? And that would work, okay? So then I just end up with, I'm going to factor out my common binomial. I guess I should be doing this, right? These are always equal to 0. So I'm going to factor out my x minus 4, and what's left behind? Well, I've got my x squared plus negative 16, right? And so this thing, we can see it factors into x minus 4, and then I could factor my x squared minus 16. That's just a difference of squares, right? So I could split that, and I end up with x minus 4 squared times x plus 4. Everybody agree? Give me a thumbs up. We all good with that? If I split the x squared minus 16 into an x minus 4 times an x plus 4, then I've got two factors of x minus 4, so that's squared. Okay, and so my zeros then end up being x equals 4 or x equals negative 4, right? Okay, so we'll go back to this other page, and we can start to, I thought I had a table going here. Did I not? I guess not. Okay, so we'll go ahead and start to build a table from this. Where's that stuff? This dumb thing. I don't understand how this thing works. Oh, there we go. Okay. There we go. All right. Okay, so we can start to build a table out of this. We had zeros, what did we say it? Positive and negative 4? Our domain is all reals. And we had critical numbers where the first derivative equals 0 at positive 4 and negative 4. So that tells us if I get 0 first derivative, we know we've got horizontal tangents. Okay, what about our second derivative? Now, if we weren't looking for points of inflection, we really wouldn't need to find the zeros of the second derivative. But let's say we are. I'd have to find zeros of this, so let's go to the next page, do our algebra on the next page. Okay, so there's our second derivative on this one. How are we going to find zeros on this one? What do you recommend? Got a quadratic equation, right?
Probably just factor this one.
Okay, we could try to factor this. We could see if we get magic numbers. right? So let's see if that works. So do we get magic numbers that multiply to AC, so negative 48, and add to negative 8?
Negative 12 and 4.
There we go, negative 12 and 4, right? So negative 12 and 4 would be my magic numbers, right? And so we can split then. Remember, we can just split this middle term and we can factor by grouping, right? So we end up then with 3x squared. I always like to put the negative one first. So 3x squared minus 12x plus 4x minus 16. And then rather than having to use like slip and slide or what's the other one called, bottoms up, those are kind of hokey. We'll just factor by grouping. In the first group, we could factor out a 3x, and we're left behind with what? X minus 4. In the second group, to have the same binomial factor, we'd factor out a 4, right? So this thing then factors into x minus 4 times 3x plus 4. So we get zeros of the second derivative where? When x equals 4 or x equals negative 4/3. Okay, everybody give me thumbs up on that. Does that make sense? And did I make any, nobody saw any mistakes there? Did it all look good? Okay, all right, so we'll plug those into our table. What was it again? Negative 4/3, is that my other one? Yeah, negative 4/3. Oops, that's supposed to be a positive 4, isn't it? And then that was a 0, wasn't it? Okay. All right, so now to find the extrema, we'll apply the second derivative test, right? We factored our second derivative, and that factored into x minus 4 times 3x minus 4, right? Yeah, that looks right, doesn't it? Okay. So there's our first derivative factor, or second derivative factor. The first derivative, I'm going to go ahead and write that in factored form, and you'll see why in a second. That was x minus 4 squared times x plus 4. So let's apply the second derivative test, right? It's always easiest to work, and this is a general rule, it's always easiest to work further down the table, right? So if we can apply the second derivative test, we'd always like to. If it's convenient to do, it makes things a little bit easier. So let's look at this 0 right here. I've got this first derivative 0, so a first derivative critical number at x equals 4, okay? So what is the sign? Whoops, did I do something wrong here? Wouldn't be the first time. Let's see, what did I do? Oh, yeah, I did. Okay, so I put the 0 in the wrong spot. This 0 isn't supposed to go there, right? My zeros of the second derivative were negative 4/3 and that's supposed to be x minus 4 times 3x plus 4. Whoops. Well, that's right. I wrote it down correctly. Okay, so then this should be my 0 over here, shouldn't it? right? So let's evaluate this thing at -4. Let's start with this critical number, and let's apply the second derivative test. So we need to know, to apply the second derivative test, we need to know what's the sign of the second derivative at -4. F of -4, F double prime of -4, sorry, is going to be, would everybody agree that's going to be negative times negative? Anybody buy that? So what's the sign of the second derivative then at -4? Positive, okay. And then what does the second derivative tell us? If I've got a 0 first derivative, so a horizontal tangent, and a positive second derivative, what kind of an extremum does that have to be? You can just make a picture with your hands or type it in chat. I'm getting pretty good at interpreting people's sign language here. Is it a minimum or a maximum? Okay, everybody agree if its second derivative is positive, it's concave up, right? It's bowl-shaped up. And if we have a horizontal tangent, then don't those two conspire to give us a minimum, right? If it's got to have positive concavity and a horizontal tangent. Okay, good, that's easy, right? We found a minimum. Now, what about this other one here, though? Look what happens. For the critical number +4, we can't apply the second derivative, right? We can't apply the second derivative test because we don't have a sign of the second derivative. It's 0. So what do? What do we do in that case? What are our options here? What do you think? What are the options? I need to know what's going on at my critical number at +4. How could I check? The second derivative is not going to work. So what could I do? Suggestions? Second derivative test doesn't apply. How about the first derivative test? Yeah, why not? We'll just revert back to the first derivative test, right? So then we could just check the value of the first derivative at some test points on either side. Well, here's one test point at -4/3, right? We've already got a value that is a 0 of the second derivative, but it's not a critical number for the first derivative. So we can just use that as a test point if we want to, right? So what is the sign of the first derivative at -4/3? Well, this is, I'm squaring that factor, right? So I'm always going to get a positive result when I square something, right? I'm going to get a number squared. And then -4/3 plus 4 would be positive, wouldn't it? So once again, let me just kind of write that down. If I do f prime of -4/3, I'm getting negative factor squared, which makes it positive, times positive, which gives me positive, right? Now I just need to check a value on the right side of +4. Like I could plug in, like 10 or something, right? If I plug in 10, f prime of 10 is going to give me positive squared plus positive is positive. Okay, so is that an extremum? It's not, is it? It's not a transition in first derivative. The function goes from increasing to increasing. So what must that be? There is a horizontal tangent there. What must it be? Type it in chat, everybody. What do you think that is it for? We got to solve the mystery. Yeah, what do we call those? I think Daisy just said it. I think so. Mike's not working, but I think she said it. What do we call those things? If we have a place where we have, what are the possibilities here? Let's look at this. Let's think of this a little different way. A critical number of the first derivative could be a maximum or a minimum, or it might not. It might be a false alarm, right? What about a zero of the second derivative? There's only one. Well, actually, it could end up being a minimum or a maximum, right? We don't know. Or it might be a point of transition of the second derivative. It could be an inflection point. Yeah, but it's got to be one of those things. So it must be an inflection point, right? How could we tell that? Well, what if we had done something slightly different? Now, we're trying to find here, if we're only trying to find critical numbers, or excuse me, maxima and minima, extrema, then working in that first derivative row, that made a lot of sense, right? That's a pretty easy way to check to see if, by the first derivative test, what is this thing? If the second derivative test fails by giving us a zero for the value of the second derivative at our critical number, right? But let's think really logically about this. There's almost an art to using these tables. If I'm trying to get everything for this function, if I want to find all the inflection points as well as the extrema, couldn't I just have, I'm going to have to choose a test point down here anyway around these zeros to determine if the concavity is changing, right? So what if I had just done this instead? What if I had said, okay, let's try a value like, how about 0, right? Because that's between -4/3 and 4. And then I already tried the value 10, but let's evaluate the second derivative at these places. So what's the sign of the second derivative at 0? Okay, we know that f double prime of 0 is going to give us negative times negative, which is, hang on, did I do that right? -4. Yeah, that's right. Negative times negative, which is positive. Okay. Did I write that thing down wrong? I think I did. Isn't that supposed to be a 3x plus 4? It is. Okay, no wonder. That didn't seem like that was working out right. That's supposed to be a 3x plus 4. And so if I evaluate this thing at -4, I get negative times negative. But if I evaluate it at 0, yeah, everybody see this? If I evaluate this thing at 0, I'm going to get negative times positive is negative. Right? Everybody give me a 1.5. You see, I had to fix that mistake. Does everybody see that? I had just written down the wrong version. That I wrote the factored form of f double prime, our second derivative, incorrectly. Doesn't change very much, but it changes the sign of the second derivative at this test point. So what is going on here then at x equals -4/3? If it's a 0 of the second derivative, and to the left of that 0, the concavity is positive, and to the right, the concavity is negative. What is that thing? What's going on there? Everybody type it in. What is that? Okay, yeah, that's an inflection point, isn't it? That's the definition of an inflection point. It's It's a place where the sign of the second derivative changes and a tangent line exists, right? Okay, so then that's an inflection point. Well, what about at 10? If I plug 10 into my second derivative, I'm going to get positive times positive, which is positive. Okay, so that sums it up, doesn't it? Now we know that right here we also have an inflection point. Okay, it's not an extremum, it's an inflection point. So did we really have to apply that first derivative test there? No, we didn't, right? So that rule that I gave you a little bit ago about it's always easiest to work further down the table makes sense. I didn't even really have to do this stuff, did I? I didn't really have to figure that out. I could have just avoided applying the first derivative test and just worked exclusively in that second derivative row, and it tells me everything. It tells me that these are inflection points, and it tells me that this is a minimum, and if this is an inflection point, it can't be an extremum, right? Everybody see that? So then what's this thing look like? Well, we ought to be able to draw a picture of this thing, right? Let's do that real quick. So make a little sketch of this. So here's x equals 0. I'm not going to draw this to scale. We've got a critical number at -4 that's a minimum. So over here, we've got a minimum. I didn't draw that very well, but you get the idea. I get at -4/3, I'm getting an inflection point, right? And then I get another inflection point at 4. So it's just doing something like that, isn't it? Right? Everybody agree? Okay. Let's see if we got it right here. Yeah. Okay, there's our picture. Okay, what about this one? We know what this looks like, right? There's just an x cubed function. We know what that looks like, but let's just show that our table can give us a sketch of this accurately. Okay, this is a little bit tricky though, as you're going to see here in a second, because the zeros of the function and all of the derivatives are going to be at the same place. Okay, the domain here would be all reals, right? How about symmetry? Is there any symmetry on this? Type it in chat if there's symmetry. Do we have even or odd symmetry on this? Okay, good. It's odd, isn't it, right? Because I mean, we could apply the test, but we know that it's a polynomial with only odd exponents. And so, yeah, it's going to have odd symmetry. So it's going to have rotational symmetry about the origin. We already can see that, right? It's going to have rotational symmetry about the origin. So let's differentiate this. We all know that our first derivative is going to be 3x squared. And our second derivative is going to be 6x. And those both have zeros at x equals 0. So x equals 0 is a 0 of the first and second derivatives. Can we apply the second derivative test here? Yes or no? Remember, second derivative test is we want to determine the sign of the second derivative at our first derivative critical number of 0. Right? We get
No, because it's also a solution of the second derivative.
there you go. Right? We can't, because even though this is a critical number, it's also a 0 of the second derivative. So the first derivative test, or excuse me, the second derivative test does not apply. I just need to know then if I'm only looking to see if this is an extremum, well, then I could apply the first derivative test, just like I did before. That's always going to work, right? Sometimes it's just a little more work. But if I'm doing something like I just want to determine if this is an inflection point, then I could apply test values of the second derivative around this 0. Either one, they both work, right? Let's pick values like -1 and +1. Well, for the second derivative, when I evaluate the second derivative at -1, I get a negative value of the second derivative. At +1, I get a positive value. So this is an inflection point, right? That's all I need to do. I don't need to apply the first derivative test. I could, but if I did, I'm just going to find out that I get positive on both sides, and it's not a point of transition, and so it's not an extremum, right? But I don't really need that first derivative row. Okay, and what's this thing look like? Well, we know what it looks like. If I evaluate the function at 0, f of 0 is 0. So I've got an ordered pair. I've got a point of inflection at the origin, and I know that it's concave up on the right side and concave down on the left side. So that we know that's what it looks like. And it does have that rotational symmetry, right? We know it's got odd symmetry. Okay, so everything falls into place. It all makes sense. Okay, what about this one? F of x equals x to the 4th. So domain, all reals. What kind of symmetry does this one have? Odd or even? Type it in chat real quick. Odd or even symmetry? Yeah, it's even. It's a polynomial with only even exponents. So it's even symmetry. So that means that it's going to fold over this axis of symmetry, right? So it's going to be that kind of symmetry where it folds over the y-axis. We can all see that the first derivative is 4x cubed. The second derivative is 12x squared. And once again, those both have zeros at x equals 0, right? We can see that f prime equals 0 at x equals 0. So when we make our table here, so what's going on at 0, 0? This time, if I check test values, the value of the second derivative is positive everywhere. So that seems a little strange, doesn't it? Positive concavity to the left of 0 and positive concavity to the right of 0, and no concavity, 0 concavity at 0. Okay, does that make sense? I mean, think about that. Doesn't concavity, think about the concept of concavity. Concavity if it's positive concavity, that means that it's bowl shaped up and that a tangent to the curve sits below the curve, right? If it's concave down, it's bowl shaped down, and a tangent line sits on top of the curve. Okay, but if I graph the function x to the fourth, let's look at this in Desmos. Right? If I graph the tangent line, oops, y equals 0, not x equals 0. And I focus in on this thing. I mean, if I focus in far enough, you can see that this thing, it is curving up, isn't it? Right? If I zoom out a little bit, I can see that this thing is curving up and the tangent does sit below the curve, right? So it really does effectively have upward concavity at 0, right? There's no place on that function where values of the function are negative. It never turns down, right? It only turns up, okay? So what do we make of this then? It's kind of a false alarm. It doesn't really make sense to say that I have this isolated point at 0 where the concavity is 0 and every place to the left or the right is positive. No, it's got to effectively be positive there too. You can't have an isolated point with no concavity, because concavity depends on the relationship of the function at x equals 0 to its neighboring points. And if it's concave up every place else, then it's concave up there also, right? Okay, just to prove that, let's look at the first derivative. If I evaluate the function at -1, the first derivative is negative. If I evaluate it at +1, the first derivative is positive. So we can see here that this is definitely a minimum, isn't it? Right? I'm going from decreasing to increasing. So it's a minimum, right? What's the moral of the story? Well, I don't know if there's one moral there, but the point is that you can work in any row of this, either the first derivative or the second derivative, to figure out what that is. But if you get a weird case like this, where you get positive concavity, 0, positive concavity, well, then effectively that's just telling us that this is really not 0. This really ends up being positive, right? If that's confusing, though, just use the first derivative test. Just work in the first derivative row. That's always available. Okay? Give me 1 to 5. How are we doing? And this thing does have, we know what this looks like. We just looked at it, right? It's got the even symmetry, like we said. Okay? Give me 1 to 5 on that. Okay? Big thing is, the reason I showed those to you, these last 3, is just because they're places where the second derivative test fails. And so you've got to go back and revert to something else. Either you're going to look at the concavities surrounding that 0 in the f double prime row, or more traditionally, you just go back and apply the first derivative test. If it's not an inflection point, then it must be, if it's not an extremum, then it must be an inflection point. It's got to be one or the other. Okay? Okay, so one more. So just to remind you what a natural log function looks like, right? That's the shape of a natural log function. So let's try something like this then. Let's evaluate this function using analysis, right? We want to find the extrema and any points of symmetry if they exist, or any points of inflection if they exist. Okay, what's the domain of this, first of all? Type it in chat here. What's the domain? Now, this is a composition of functions, right? I've got a log of the polynomial 3x squared plus 1. Okay. We know that for a log function, the domain of log x is all positive numbers, right? X has to be greater than 0. In other words, the input to a log function has to be greater than 0. So here we have to ask ourselves, are there any values of x that would violate that? Right? Are there any values of x that are going to make this argument of the log function something other than a positive value? Right? This is the argument of the log function. Are there any? We'd have to just, let's ask the math gods. Let's solve for all the places where 3x squared plus 1 is greater than or equal to 0, because that's what has to be true, right? A log, not equal to, has to be greater than 0, right? Whatever I'm inputting into a log function has to be greater than 0. Are there any cases where that's not true? None, right? Right, we know that no matter what here, when I end up squaring x, I'm going to get a positive value out of this, right, for x squared. Or if I plug in a 0 for x, I get 0, but I'm adding 1 to it, right? So we know that 3x squared plus 1 is greater than 0 for all x, right? So my domain, in other words, is all reals. What about symmetry? Well, I mean, is there going to be symmetry on this one or not? We'll have to just apply the test. What happens when I evaluate this function at negative x? Negative x squared, the quantity negative x squared is just x squared, isn't it? Right? And that's just f of x. So this thing should have even symmetry then, shouldn't it? Right? The way we might say that in math is the function f of x is insensitive to the sign of x. It doesn't matter if x is positive or negative, I'm getting back the same result. Everybody agree on that one? Okay, so we do have even symmetry. Okay. All right, so we got to find critical numbers. It's been a while since we've differentiated a log function. How's that work? If I calculate f prime, what do I get back? What's the derivative of log u? Well, u prime over u, right? 1 over u times u prime. Okay, well, let's write that down. Remind ourselves about that. So we know right? We haven't used that in a while, okay? So that's just going to give us u prime. What's the derivative of, what's u prime? So u is 3x squared plus 1, so just 6x, right? Divided by u, 3x squared plus 1. Okay, there's our first derivative, right? Is our first derivative undefined anywhere? Look at that first derivative. Is that undefined anywhere?
No.
It's not, is it? It'd be undefined where the bottom is 0. Agreed? And the bottom can never be 0. We already established that 3x squared plus 1 is always positive valued. It's always, right? Always greater than 0. So it's nowhere undefined, but f prime equals 0 when x equals 0, right? Okay, what about the second derivative? If they're asking us about concavities, so if we were just looking for extrema, would I bother taking the second derivative here, do you think? If I were not looking for concavities or inflection points, would I bother taking the second derivative? Differentiating again. No. What would be the only advantage of taking a second derivative there? It would just be to be able to apply the second derivative test, right? But I don't need to. I can apply the first derivative test, right? So we only take the second derivative when we have to. You know, if we're finding inflection points or concavities, then we have to, or if it's easy and useful, right? If the second derivative is just a slam dunk, if it's easy to do, then we'll take it and apply the second derivative test. But otherwise, we wouldn't take the second derivative unless unless it really was simple or we had to. Okay, but in this case, we have to. So we got quotient rule, right? So I've got low D high minus high D low divided by low squared, and we'll have to finish this up next time. All right, so keep plugging away at it. If you're having troubles, please come see me after school and get some questions answered. Okay, I'm here every day. It's a simple thing to do. You know, it's quick and easy. So come see me.